Hello and welcome to another stats review video. All right, so some of these questions are going to look pretty familiar. They're either coming from old exams or similar to problems on old exams, but it just gives you another chance to kind of hear the explanations, see how they work, and get yourself ready for the actual final. So, number one here says calculate three conditional distributions for opinion of the band, one for each age group. You may present your results in either a table or a graph. I'm just going to make a table here, but we're calculating conditional distributions for opinion of the band. So our percentages are going to be percentage like, percentage dislike, percentage uncertain, right? Because our distribution is for opinion of the band. And then we're going to do one of these distributions for each age group. So for 11 to 14, we want to know what percent like, what percent dislike. For 15 to 18, we want to know what percent like, what percent dislike. And for 19 to 22, we want to know what percent like and what percent dislike. All right, so since we're doing it from each age group, that means that we're going to be going across our table. All right, so if we kind of say that this row is going to be our like row, this row is going to be our dislike row, and this row down here will be our uncertain row. All right, then for the first one, it's 18 out of 63. The next one would be 30 out of 63. And then the last one would be 15 out of 63. And then if we're converting those to percentages, it's like 28.57%, 47.62%, and 23.81%. And then usually, if you've got the first one set up right, you're probably going to get the rest of them right because you're going to follow that same pattern. But it's making sure you get that first one set up right. So now 15 to 18, we just drop down a row, and we're going to do these right here. So 38 out of 65, 10 out of 65, and 17 out of 65. And again, let's convert those over to percents. 58.46%, 15.38%, 26.15%. And then again, one final time here where we're doing 40 out of 122, 67 out of 122, and 15 out of 122. So 32.79%, 54.92%, and 12.30%. And again, these might not add up directly to 100 because of rounding here and there. But all of them are kind of, notice that each one should add to 100 roughly, all right? So there's your one distribution for 11 to 14. There's your next distribution for 15 to 18. There's your last distribution for 19 and 20. All right. Number two here, the local post office weighs outgoing mail and finds that the weight of first-class letters is approximately normally distributed with a mean of 0.69 ounces and a standard deviation of 0.16 ounces. What is the 60th percent of first-class letter weights? So that means that 60% are below this value, which basically means we're going to use an inverse norm and say we want to know the value for which 60% of the area is to the left and we're going to tell you that the mean is 0.69, and we're going to tell you that the standard deviation is 0.16. All right, so when you saw this problem earlier in the year, you had to do the z-score formula, but at this point in the course, you can just do it all on the calculator and say, okay, 60th percentile when the mean is 0.69 and the standard deviation is 0.16, and you'll get an answer of 0.7305 ounces. First class letters weighing more than 1 ounce require additional postage. What proportion of first class letters at this post office require additional postage? So this one was asking for a weight. This one's asking for a percentage. So we're going to be switching over to NCDF from 1 to 9999 when our mean is 0.69 and our standard deviation is 0.16. All right, so again, these questions should look familiar, but you get to do them a slightly different way now that we're further along in the course. All right, so 0.69, 0.16. All right, and we end up with 2.63%, 0.0263, or 2.63%. All right, let's look at the back here. For the data below is the number of unprovoked alligator attacks in Florida each year for a 33-year period. Construct a histogram for the distribution, choose an appropriate bin width, and be sure to label and scale in axes for each one. All right, so remember, you're kind of creating these baskets and you're counting how many fall in each basket. So you might have a basket that's, 1 to 4, and you might have a basket that's 5 to 9, and one that's 10 to 13, and so on and so forth, or whatever you end up deciding to use. Hold up here. Your bin should always be the same size, so I goofed up here. This should be 5 to 8 if I'm making everything the same size. And this should be 9 to 12 so that everything is always the same size. So each one has 4 values in it. 1, 2, 3, and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 to 16, 17 to 20, 21 to 24. And is that going to be high enough, or is there anything above that? Nope, that should get everything that I need there. All right, so then it's just a matter of going through and counting how many fall in each bucket. Now, I'm not going to make you watch me count these, but basically there ends up being 6 values that are between 1 and 4. There ends up being 8 here, 6 here, 6 here, 5 here, and 2 here. And notice those add up to 33 because I had 33 observations in total. So now when I'm ready to make my actual graph, the vertical axis is just the counts. It's what I just counted. The bottom axis would actually be my alligator attacks per year. And then I can either write it as like 1 to 4, or usually the way we do it is I would make my first bar here and say this is 1, and it goes to less than 5, right? Because by going to less than 5, I basically know that's 1, 2, 3, or 4, because there's no decimals here. And then the next one can go to less than 9, and then less than 13, less than 17, less than 21, and less than 25. All right. And then hash marks 1, 2, 3, 4, 5, 6, 7, 8. So the first one goes up to 6. So there's my first bar. The next one goes up to 8. So there's my second bar. And then the next two are at 6. So they're going to stay the same height here. And I've got one at 5, so that's a little bit lower. And then one down here at 2. So right there. Okay. So that's what your histogram could look like. This is based on a bin width of 4. Right? If you choose a different bin width, you're going to end up with a slightly different result. But again, it's kind of creating these baskets, counting how many are in each basket, and then using those counts to actually make the graph. All right, based on your histogram, what numerical measures of center and spread would be best used for this distribution? It seems that this distribution is sort of skewed to the right. So when something is skewed to the right, you're better off using as your measure of center the median, and as your measure of spread, you're better off using the range and the IQR. If it had been symmetric, then we would have done mean and standard deviation. So just a side note here is that when something is symmetric, that's when we use the mean and standard deviation. When something is skewed, so there's that little note there, side note. When something is skewed like it is here, we use the median and the range and the IQR to measure the spread. Okay. And again, your graph could look different based on what you chose as your bin width, but you shouldn't be choosing like a bin width of 1. All right. It should at least be, greater than 1. And how large it is really depends on your data set. All right. Let's look at the next sheet. All right. Wile E. Coyote is pursuing the Roadrunner across Great Britain towards Scotland. The Roadrunner chooses his route randomly, such there's a probability of 0.8 he'll take the high road and 0.2 he'll take the low road. If he takes the high road, the probability that he gets caught is 0.01. If he takes the low road, the probability he gets caught is 0.05. Find the probability that he took the high road given that he was caught. All right. So let's take a look at this. He can choose either the high road or the low road. All right, so that's our first choice, high road or low road. He takes the high road 80% of the time. He takes the low road 20% of the time. All right. If he takes the high road, he can either be caught or he can escape. If he takes the low road, he can either be caught or he can escape. Now, let's see what the problem is telling us. It says if he takes the high road, the probability he gets caught is 0.01, which means the probability that he escapes must be 0.99. If he takes the low road, the probability he gets caught is 0.05, which means the probability that he escapes is 0.95. All right. Find the probability that he took the high road given he was caught. So this is the probability of the high road given he was caught, which then requires our conditional probability formula, which takes the given and puts it at the bottom of our fraction, so the probability of being caught, and the top of our fraction is these two ANDed together. So the probability of taking the high road and getting caught. So to find the probability of getting caught, we have to use this branch and this branch. And then the probability of taking the high road and getting caught is just this branch right here. So it's basically this one over these two added together. So that leaves us with 0.8 times 0.01 over that same thing plus 0.2 times 0.05. All right, so these two branches added together is the bottom, and this branch is the top of our fraction. So what is that going to give us? It's going to give us 0.008 over 0.018, which is going to end up giving us, let's see, where's my calculator? 0.008 divided by 0.018 is a bunch of fours. So 0.4444. All right, so that would be our final answer there. And of course, you could always write that as 44.44% if you wanted to. All right, but again, making a tree, using that tree to help analyze a conditional probability, and then plugging things in where they belong. ACT scores for about 1 million high school graduates followed a normal distribution with a mean of 20.9 and a standard deviation of 4.8. Choose two students independently and at random from this group, X and Y. What are the expected differences in their scores? What is the standard deviation of the difference in their scores? All right, so if both of these have the same mean, they're both a mean of 20.9, and we do the expected value of X minus Y, it's just the expected value of 20.9 minus the expected value of 20.9, or 0. The standard deviation, we learned that you have to add the variances. Even if you're subtracting, it doesn't matter that you're subtracting, we still add the variances. So that's going to be 4.8 squared plus 4.8 squared. And then to turn it back into a standard deviation, we're going to take the square root. And that ends up being like 6.7882. This says, find the probability that the difference in the two students' scores is greater than 6. Right? Now, that could be greater than 6 in a positive direction, or that could be greater than 6 in a negative direction. So we're going to do an NCDF from 6 to 9999 when the mean is 0 and the standard deviation is 6.7882. And we're going to do an NCDF from negative 999 to negative 6 when the mean is 0 and the standard deviation is 6.7882. Right? Because again, it could be that X is 6 points higher, or it could be that Y is 6 points higher. Right? So we want to look at it in both directions. And now these are actually going to give us the same result because, again, the curve is centered at 0. So we could just do one of them and double it, but I'll show you that you get the same result. So 6 to 9999 when the mean is 0 and the standard deviation is 6.7882. All right, so that gives us like 18.84. And then if I do the negative version of that and go from negative 9999 to negative 6, that gives me the same exact result. So both of these give me basically 1884. Again, because the curve is symmetric. So I can really just take this answer, double it, and that'll be my final result. All right, so 0.3768 would be the final answer for this question. Okay, but again, combining random variables and then using it inside of an NCDF. High blood pressure adds to the workload of hearts and arteries and may increase the risk of heart attacks. If not treated, the condition can also lead to heart failure, kidney failure, or stroke. We wish to test the effectiveness of ACE inhibitors as a treatment for high blood pressure. It is well known that men and women react differently to common cardiovascular drug treatments. What sort of experimental design would you choose for this study and why? All right. So again, this is your knowledge of experimental design and data collection. So this would be a randomized block design. And the reason we would choose it is it allows us to create different groups for men and women to help control for that factor in our results. All right, explain why an experiment involving 600 men and 500 women is preferable to one involving 60 men and 50 women, right? Increasing the sample size decreases the chance of getting highly unusual results due to sampling variation. All right, in short, it makes your findings more reliable. Assume that 600 men and 500 women suffering from high blood pressure are available for the study. Describe a design for this experiment. Be sure to include a description of how you assign individuals to treatment groups. Right? So again, this is just describing your experimental design, showing me that you know how to divide people randomly and write up, a set of instructions that pretty much anybody could follow to properly set up what's going on here. So we'll start by saying, run the experiment with two groups, males and females. And then we can say, for the males, generate 300. And you can either say unique random numbers, or you can use the phrase ignoring repeats. But either way, you should use one of those two terms to say what happens for when you generate the same number. Right? So basically, we have to either generate unique numbers or we have to ignore repeats from 1 to 600. These numbers are the control. The other 300 are the treatment group. All right. And then the second group, you can shorten it up a little bit because it's pretty much just the same thing. So I'm just going to say follow the same process for the females, only each group will have 250 people, and the random numbers will go from 1 to 500. All right, so that's about the level of detail that I'm looking for on one of these. Don't just say, oh, I'm going to divide them up into two groups and have a control and a treatment. You've got to give me a little more detail. You've got to show me that you're randomly assigning them somehow. You got to show me that you're acknowledging that you could have like repeats and that how you're gonna deal with that, so that really anybody could kind of pick this up and have a pretty good handle on what they need to do to carry out your experiment. All right, let's move on to the next sheet. All right, so a local newspaper in a large city wants to assess support for construction of a highway around a business district to reduce traffic. They survey a random sample of 1,152 residents and find that 543 support the bypass. Construct a 95% confidence interval to estimate the proportion of residents who support the construction of the bypass. All right, so again, this is going to your menu here and being able to pick out what you actually need to use, because you do not have to do these by hand. So first of all, it's a confidence interval, so we're down here. Second of all, we only have information about one group of people or one group of individuals or one group of whatever, so that rules out all the twos. All right, we never use z-interval, so now we're t-interval or one prop, and this is being presented to us as a proportion. All right, 543 out of 1152. That's a proportion. So we're going to be using one prop z interval. All right, it's going to ask for an x, which in our case is 543. It's going to ask for an n, which in our case is 1152. And it's going to ask for a confidence level, which we're doing at 95%. So we end up with 0.44253 to 0.50018, which is basically saying, we are 95% confident the true value is between, and I'm going to round here, but basically 44 and 50%. All right. Again, the sample result was 47%. That's the middle of our interval. That's our sample result. That's the 543 divided by 1152. But we have to go above and below that to come up with our interval. And our interval stretches down to 44 and goes up to 50%. All right, Guptill Skate Park in Latham is thinking about expanding their Secret Dance Club. To assess support for this plan, they will select an SRS of middle school students and ask if they are in favor of an expansion. They expect 70% of the student body to say yes. What sample would be required for a 90% confidence interval with an approximate margin of error of 0.04? All right, so these are those sample size questions. All right, so we need our sample size formula, which is that the margin of error equals z star. And then because this is proportions, we're using this formula right here, PQ over N. If it had been not proportions, we would have done this one, M equals Z star times the standard deviation over the square root of N. But this one's dealing with proportions, so we need to deal with this formula right here. And then we just start plugging things in. Margin of error is 4%. Z star we have to find by doing inverse norm. So this is going to be an inverse norm. And if there's 90% confidence interval, there's 10% left over. But that 10% is split between the left and the right. So we only put 5% in our inverse norm. And then because this one tells us they expect 70%, we're going to do 0.7, 0.3 over N. When they don't tell you a P and a Q, worst case is that P equals 0.5, right? But in this case, they give us a value, so we're going to use it, and then we just go from there. So inverse norm of 0.05 gives us negative 1.64, but we ignore the negative, so we've got 1.64 times the square root of 0.7 times 0.3 over the square root of n. Multiply both sides by the square root of n. And you've got this right here. And then at this point, I'm just going to go and do the rest of it on the calculator. So 1.64 times the square root of 0.7 times 0.3. I'm going to divide that by 0.04. And then I'm going to square that and get 353.01. And for these questions, we always round up. So this would be 354 people. Because if you round down, technically, you're going to be above this margin of error, and you'd rather be below it. All right, so 354 people. But again, knowing this formula and then being able to kind of work through it and get whatever you need to get to. All right, take a look at the back. A soccer player succeeds in scoring a goal on 84% of his penalty kicks. Assume that the success of each kick is independent. In a series of games, what is the probability that the first time he fails to score a goal is on the 5th penalty kick? So if he makes it 84% of the time, it means 16% of the time he must miss. So this is saying, all right, you made 4 in a row, and then after you made 4 in a row, you missed one. So the probability of making it is 84%, and we need to have that happen 4 times. The probability of missing it is 16%, and we need to have that happen last. All right. So if we work this out, 0.84 to the 4th power times 0.16 is 0.0797. 0797. Now, you could use the geometric PDF on your calculator. That will do the same exact thing. So I could go here, do geometric PDF. Again, the probability. Now, you have to be careful here because, yes, he makes it 84% of the time, but we're saying really we're counting how many times until you miss. So the probability that we'd be using in here is 0.16. And we want to know what are the odds of it happening on the 5th try. And you're going to see you get the same result. All right, so I don't care which way you do it. Just make sure you're getting to the right spot in the end. What is the probability that he scores on exactly 6 of his next 10 kicks? All right, so this is a binomial situation because they're giving us a fixed number of trials. All right, this is the number of trials. This is the number of successes. So this is a binomial, and because it says exactly 6, it's going to be a binomial PDF. If it had said 6 or fewer, that would have been a CDF. All right, that's what CDF does. It does from the number down. But this is just a binomial PDF. So we've got 10 trials. Let's go and bring it up so you can see it. It's in the distribution menu. We've got 10 trials. The probability of making it this time is the 84% because now we're back to making, not missing. And we want to know what are the odds of making exactly 6. And we'll see that it's 4.83%. So 0.0483. And again, you can always write that as a percent if you so choose. All right. The weight of eggs produced by a certain breed of hen is normally distributed with a mean of 65 grams and a standard deviation of 5 grams. Calculate the probability that a randomly selected egg weighs between 62.5 and 68.75. All right, so this is just a straight NCDF. And again, so we want to know what are the odds of being between 62.5 and 68.75 when the mean is 65 and the standard deviation is 5. All right, so again, we've got a little curve here. The curve is centered at 65. We want to know what area are we looking at right here? All right, so distribution, normal CDF, 62.5, 68.75, and the mean is 65, the standard deviation is 5. That'll give us 0.4648. All right, so 46.48%. And then part B says, think of the carton of such eggs as an SRS of size 12 from the population of all eggs. Calculate the probability that the mean weight of the eggs in the carton falls between 62.5 and 68.75. So we're now coming up with our sampling distribution. All right, and the mean of that sampling distribution, the mean of all of the X bars, is going to equal the population mean, which is 65. The standard deviation of that sampling distribution is going to be the standard deviation of the population divided by the square root of n. So in our case, that's 5 divided by the square root of 12. So, sorry, the paper wasn't high enough there. Sampling distribution, mean of X bar is going to be the population mean, which is 65, and then there's that. So 5 divided by the square root of 12 is going to be 1.44. All right, now that we have this, we can now do a normal CDF or a normal NCDF on these values. All right, so same start to our NCDF is right up above, 62.5, 68.75, but now we're dealing with a standard deviation of 1.44 instead of the standard deviation of 5. All right, this was for an individual egg. This is for 12 eggs. All right, and when you've got 12 eggs and you're averaging them together, you expect those averages to be a lot closer than you expect an individual egg to be. All right, so if we put that in there, we should expect a lower percentage, and let's see what we get. 62.5, 68.75, 65, and then change this to 144. And we end up with, oh, sorry, I didn't mean a lower percentage. We're going to end up with a higher percentage because our standard deviation is that much smaller, all right, which means we're more condensed. So our curve is not as spread out. So because our curve is less spread out, this represents a much wider range, and we're going to capture more of the area. All right, so if that was our original curve, our new curve is much more narrow, but since we're still going out to those same values, we're now capturing a much greater percentage of it. All right, so this is going to be 0.9541, which is your final answer, but you could also call it 95.41%. All right. So again, yeah, this is creating a much more narrower curve. And since we're using the same exact range, that narrower curve is going to be a higher percentage than it was here, which had a wider curve. All right. Less area outside of this range compared to up here. All right, let's take a look at the final sheet here. So, have older cell phone users caught on to this new fad called texting? Separate SRSs of people under 30 and over 30 were asked whether they made more phone calls or sent more text messages on their cell phone on a typical day. Here are the results. Give the name of the appropriate chi-squared procedure, homogeneity or independence, and state the null and alternative hypothesis for the test that will address this question. All right. So which one is this? All right. Notice that they tell you there were separate random samples. So when you have multiple samples, that's the chi-square test of homogeneity. All right, and again, the reason for that is multiple samples. And when we're writing that null, it's going to be the distribution of, we'll say, phone habits is the same across both groups. So there's no difference, because remember, our null is always the statement of no difference. And the alternative will be that the distribution of phone habits is not the same across both groups. Okay. Says carry out the test with a significance level of 5% and state your conclusion. So our alpha is going to be 0.05. We're going to be doing the chi-squared test on our calculator, which means we're putting this into our matrix. So we can go to our matrix menu. We can go to edit. I've got to clear out what I have in there. So whoops, not 22, just 2 by 2. And then let's see, 146, 32, 34, 98. All right, so I've got those values in there from my table. I then go to stat tests. I'm doing the chi-squared test, not the goodness of fit test, the chi-squared test. All right, my observed is A. It's going to put my expecteds into B. That's fine. And then you'll see that it gives me my results. So my chi-squared statistic is 98.54, which is a pretty big number. And then my p-value, be careful there. That's an e to the negative 23, so that's scientific notation. I'm not going to write out all of those zeros. I'm just going to write it as 3.18 times 10 to the negative 23. But remember, your p-value is a percentage, so it would never just be 3.18. That's 318%. It's always going to be between 0 and 1, and in this case, it's really close to 0 because that's a super, super tiny number. And then the degrees of freedom are 1 there. It's the number of columns minus 1 times the number of rows minus 1. So in this case, 2 minus 1 times 2 minus 1, which gives us 1. So based on this really tiny p-value that we got, our p-value is under 5%. So we reject the null and accept the alternative. All right. So what we're saying here is that the distribution of phone habits is not the same. People that are under 30 are using their phones in different ways than people that are over 30, which I think most people would probably intuitively agree with. All right. Economists often track unemployment by measuring the proportion of people who are underemployed, meaning they are either unemployed or would like to work full-time but are only working part-time. In the summer of 2010, 18.5% were underemployed. The mayor of Vicksburg wants to show the voters that the situation in their town is not as bad as the rest of the country. His staff takes a simple random sample of 300 residents and finds that 48 of them are unemployed. All right, so this is sort of the population. And then this right here, 48 out of 300, which happens to be 16%, is the sample result. So do the data give convincing evidence that the proportion of underemployed in Vicksburg is lower than in elsewhere in the country? Support your answer with a significance test. So they took a sample, they got 16%, the population value is 18.5%. is that a big enough decrease that we have convincing evidence? So the way we handle this is we set up a null that P is still 18.5%. And then since we're testing to see if we're lower, our alternative becomes that P is less than 0.185. And then our alpha is going to be 0.05. All right. Now we're going to bring up our menu. This is a hypothesis test. We don't have two different samples, so that rules out all our 2's, and that leaves Z, T, and one prop. We never use Z, so that leaves T and one prop. And because we're dealing with proportions here, it really only leaves the one prop Z test. So our null is that P sub 0 is 185. So let's fill this in on our sheet so that we get full credit. So we're using the one prop Z test. Our null is that P is 0.185. Our number of successes is 48. Our sample size is 300. So let's fill in those. And we're seeing whether we are less than the null. All right, so we hit calculate. It gives us a test statistic of negative 1.11. It gives us a p-value of 0.1324. All right. And then based on that p-value, our p-value is over 5%. So we fail to reject the null. All right, so in this case, we don't have enough evidence to say that the unemployment is actually better in Vicksburg, right? It's close enough that we basically say, yeah, we can't say that this is wrong, right? Your town might be just as bad as everybody else, right? But again, being able to use that menu, being able to select the right choice, and then being able to correctly analyze your results, whether it's a chi-squared, whether it's a proportion, whether it's a t-interval, you're still interpreting these p-values in the same way. All right, final question, and then we are done. A study of iron deficiency among infants compared blood hemoglobin on a random sample of 1-year-old infants who had been breastfed to a random sample of 1-year-old infants who had been fed with formula. Here are the results. All right. We wish to test the hypothesis that UB minus UF is 0 against UB minus UF is not equal to 0, where UB and UF are breastfeeding versus formula. All right. Assuming the conditions have been met, calculate the p-value for your test. All right. So we don't have to worry about conditions. We can just jump straight to performing the hypothesis test. So again, it gave us the null. It's showing it the subtraction way. You could also write it like this. We're saying that the two means are equal versus we're saying that the two means are not equal. So basically, we're testing, is there a difference with how you feed your baby? And then again, we've got these summary statistics up here. This is our X bar. So these are our sample means. And this is our S of X. So these are our sample standard deviations. All right. So again, we're going to that same menu. This time we do have 2 samples. All right. So that brings us to one of the choices with 2 sample Z, 2 sample T, or 2 prop. All right. These aren't proportions, and we never use the Z tests. All right. So that automatically limits us to the 2 sample T test. 2 sample T test. All right, we don't have data here. We just have stats. So we're going to use the stats feature. X1 bar is 13.3. SX of 1 is 1.7. And then N1 is 23. So let's type those in there. 13.3, 1.7, 23. And then x bar 2 is 12.4. S of x2 is 1.8. And n2 is 19. So 12.4, 1.8, 19. And then the problem told us that we were choosing not equal to this time. Okay. So once that's all in there, again, pooled versus not pooled, we never pool, so we can just leave that as no. So we'll say pooled, no. But we never pool. That's like a relic of a time before better calculators. So we're not going to pool. We can hit calculate, and then that's going to give us our results. So our test statistic is going to be 1.65. And then the p-value that results from that test statistic is 0.1065. All right, so there's our p-value. It says, interpret the p-value in context of the study. Draw the appropriate conclusion at the 0.05 significance level. So what this is saying is there was a 10.65% chance of getting an observed difference of 0.9 or greater, right? Because the gap here is 0.9. That's the observed gap. So there was a 10.65% chance of getting observed difference of 0.9 or greater if the true difference is 0. All right. So as such, we fail to reject the null because our p-value is above 5%. And then last but not least, C says, given your conclusion in part C, what type of error have you possibly made? Describe the error in the context of this study. So remember, a type 1 is when you reject and you're wrong. A type 2, type 1, I didn't actually write my 1 there. A type 2 is when you fail to reject and you're wrong. All right, so in this case, it's impossible to make a type 1 error because we didn't reject the null. All right, a type 1 error is when you reject the null and you're wrong. All right, we didn't reject the null, so we can't have made a type 1 error. It's possible we made a type 2 error, right? Because we failed to reject the null, but it might be that we're wrong. It might be that there is a difference between breastfeeding and formula feeding, and we just haven't picked up on it or realized it. All right. So in the context of this study, what does that mean? It means we think there's no difference between breastfed infants and formula fed infants, but we're wrong. All right. So again, this idea of being able to go into that menu, choose this correct test, and then not just regurgitating the numbers, but actually being able to understand and interpret what those numbers are saying and how they relate to everything we just did. All right. So again, this is just a lot of these problems you've seen before. They're not necessarily new, but just one more sort of review resource for you. So we've got, two sample hypothesis testing. We've got chi-squared test. We've got one sample tests. We've got combining random. We've got sampling distributions and using NCDF. We've got BPDF, GCDF, BPDF, and G. We've got sample sizes. We've got confidence intervals. We've got experimental design. We've got, conditional probability. We've got combining random variables. And then all the way back to the beginning of the course, we have things like histograms, describing distributions, conditional distributions, and CDF type problems. So again, a lot of material, but it's a full year course. So hopefully these just give you, another resource, another way to review, and help you get ready for the final exam. All right. Have a great day, and I will see you when I see you. All right. Bye.